A reminder before we start that we have been talking about two very different things that share a symbol and also kind of share a name. They're very different though, definite integrals and indefinite integrals. The indefinite integral, those are antiderivatives. We've learned a few ways to find those. We'll do a lot more later in the year, but we're actually kind of setting that aside for a while. Another topic, which is a completely different idea, it just shares a symbol and a name, is what we call a definite integral. The definite integral, remember, is the product of the y value, the changing y value, and x distance. So we saw this with some examples much earlier in the year, where we would have a function whose y value changes. And if I wanted to know the definite integral from a to b of whatever this function is, we'll call it f of x. It's the product of every y value times the overall x distance, but since the y value changes, it's a little bit complicated. What we did was we kind of thought of that as area of this whole shape here. And we thought of the definite integral as the signed area. And we're okay thinking of it that way. Our problem was calculating it. So the only method we really used earlier this year was we talked about counting boxes. If I had like a grid, graph paper underneath this, we could count boxes and use that to estimate the definite integral. We need to do a little bit better than that. So one strategy that we're going to talk about today is if I just made a bunch of estimates of nice, pretty easy shapes, like if I were to calculate the area of that, and that, and that, if you notice how I'm not missing too much. I have like I missed a little bit of the yellow here, here, and here, but I had some extra there and there, so it all balances out a little bit. It's a really pretty good estimate. What we're going to talk about today is how we can classify and name this calculation and how we can use a couple of different forms of it. That calculation, the idea of using all of these nice and easily calculable products, which show up as rectangles, to estimate the overall definite integral is called a Riemann sum. Actually, forget about the integral for a minute. Just the products themselves is called a Riemann sum. Here's the fancy notation for it. The Riemann sum is the sum of a bunch of y values at times a bunch of x distances. So notice that that's the same two pieces as are in a definite integral. A y value times an x distance. The notation looks a little bit weird here, this little I thingy here. That's just what we call an index. So when we say f of c sub I, that just means first we're going to use one x value to find the y, then we're going to use a different one, and then a different one until we've used enough. So I'll give you a little sketch of an example. Similar to the last one, here's f of x. And so what we would do to calculate the Riemann sum is divide up, so here's my a to b. Divide that space up into a bunch of different components. So I'm going to chop it up here. I'll use 3 components. Why not? And for each one of those, so the n here is the number of intervals, or I should say of sub-intervals. So in this case, it would be 3. So what I'm going to do is take 3 y values. The y values I'm going to take come from different x values. Those x values are the c sub I, different x values. So this right here could be c sub 1. And maybe right here would be c sub 2. And you know what? I'm going to make this one be my c sub 3. There's no rhyme or reason to the ones that I picked. The key is that each one, though, is within the interval, each of the three intervals. So what we're going to multiply is the y value at that spot. So I just need to find the y value. I'm going to follow that up here. That's the y value. And I'm going to multiply that y value times the x distance of the entire interval. This is the delta x. And the height of this rectangle is the y value, f of c sub I. And then I'm going to do it again at another y value. I deliberately made these that went too far. I deliberately made these very different widths just to show you that the widths do not have to be the same. They can be the same. My third y value is going to come from plugging in the third x value onto the function. And so you can see each one of those products ends up being the area of a rectangle, because the area of a rectangle is the product of the height times the width, the y value times the x distance. That's what we call a Riemann sum. The way we turn this into a definite integral, because it is clear that the area of these three rectangles isn't going to exactly equal the definite integral, because like we saw before, I missed that part, I had that part extra, I missed by a little bit. There were all these places where I was wrong. Maybe they balance out a little bit in the end, so my guess is pretty close, but it's not perfect. What we would do to make it be a perfect expression of the definite integral is to imagine that I divided that space up into more intervals. If I would have chopped it up into more intervals, say maybe I would have made another one here, you can see that a lot of that, the space that I missed before that I highlighted, a lot of it is fixed because now it's part of a rectangle. Well, if I just do that an infinite number of times, in other words, think about approaching an infinite number of rectangles, then my Riemann sum would actually equal the definite integral. And so what I'll just do is write that Riemann sum out simply as the limit. Notice how other than the limit, this expression and this expression are the same thing.